Welcome to Math 31. This is a lesson on second derivative analysis. So in the graphing section for this unit, we've looked at first derivative analysis. We've also done some work with the asymptotes. And now we're going to turn our attention towards something that's fairly new, and that would be the analysis of the second derivative and what it tells us about the graph, or a graph. And this is the key idea. Concavity, which is related to the second derivative, and points of inflection, which are often written as poi. And this graph, just a simple cubic function like this, will illustrate what the second derivative does and what it tells us about the behavior of a graph. And I've got 5 points indicated, C being at the origin. And what I'm going to do is compare the tangent lines, or the slopes of the tangent lines. So compare the slopes of the tangent lines at various points. So first, if you take a look at somewhere in the interval AB, there's a slope, there's the tangent line, so we can see what the slope looks like roughly there. But then if you take a look as you get closer and closer to C, and then right on C, if you were to describe the behavior, you would say that in the interval AC, that the slopes are decreasing. They're getting less steep. At least these ones that are in the positive way. So like the slope at point A, or the first derivative if you like, would be a fairly high number. It's a fairly steep tangent line. Point B, that slope is less. And then in the interval BC, it's flattening out even more. And finally at C, the slope is equal to 0. So let me make a note on this. That is the first derivative values are decreasing. And then, if you were to go on further, in the interval just past C, CD, the slope is increasing now. It's positive, and then in past D, it continues to increase, and then finally towards E, it's even steeper. So in the interval from CE, the slopes are increasing. So that is f prime at x values are increasing. So in the course of this function, at least as far as we have it graphed, the first derivative values were decreasing until you got to point C. At point C, they reversed and they started to increase. So point C is important. So point C is what we call a point of inflection. And this point of inflection would mean concavity changes. Now, this is going to be defined as well in the next slide. And then concavity, what does this mean? Well, we would say in the interval AC that this graph is concave down. And concave down, often just CD. And then in the interval CE, and actually beyond, we would describe this as concave up. Now, a few ways to make sense of that are that by inspection, because this graph sort of, or for an AC, the cup is down. So the cup is down means it's concave down. You see it sort of opens downwards, whereas from CE, it opens upwards. So it's got the upward shape like this. And what's really happening is the rate of change of the first derivative is shown or reflected in the second derivative. Because remember, the derivative is, any derivative is measuring the rate of change of the function that is being differentiated. And when we have the first derivative, and then take the derivative of that, that's the second derivative, it will be measuring the rate that the first derivative is changing. So if the first derivative is increasing, such as it is in CE, it produces a graph that's getting steeper, or a tangent line's getting steeper all the time, which forms the classic concave up shape. And then the reverse would be true if it's decreasing. So let's take a look at the definition then, and I've already given you this, but a point of inflection is where the concavity changes. So illustration, if you took a look at this curve, whatever the shape is, we would describe it in this interval there as being concave down, or this first interval, concave down. So you can see if you even were looking at the tangent lines, really roughing them in. Now we don't care about the fact that at the very top of this graph, the derivative, the slope of the tangent line is 0, but we do see that it's still decreasing all the way. It started off as positive, so y prime is positive there, y prime is 0 there, and then y prime is less than 0 there, and then so on. And then it's changing again, because it's getting steeper. Now y prime is equal to 0 again, and now y prime is positive. So the first derivative, the slope of the tangent lines, is changing throughout this graph. And the points of inflection is where it actually changes. Now do not confuse these with the maximum and minimum points, because they're not the same thing. They are going to, the points of inflection are going to be where it changes. So like right here, this point is what we would call a point of inflection. And the easiest way to do it is see that the graph at that point up to there is concave down, but in this next section it's concave up. So the cup is up. And then it switches to concave down, so we get this point of inflection right there. And the point of inflection is related to the second derivative, or is found with the second derivative. And it just measures what's happening with the slope of the tangent line, not what it is, because we don't care if it's equal to 0. We just care whether it's increasing, whether it's getting more steep, or whether it's getting less steep. So it's a little harder to visualize than is the first derivative, but you get good at it. And then I finish this one off there. So leading us to second derivative analysis. And this summarizes what we've got. Given any function y is equal to f at x, if the second derivative is greater than 0, that is positive, then the graph is concave up. And you've seen this before, previously in the first derivative analysis. But if it's positive, then we get the smiley face like that. So concave up. Now we used it to recognize whether a critical number was a max or min, but it's a general part of second derivative analysis. Just like if the second derivative is negative, below 0, the graph is concave down. So we get the sad look. But the mouth will show the behavior of the graph in terms of concavity. Now, if the second derivative is equal to 0, or if the second derivative doesn't exist, then x is a point of inflection. So that's what we're going to be doing, is getting the second derivative, setting it to 0, and then identifying the point as a possible point of inflection or not. So we do it the same. The method is the very same as the first derivative analysis, except that instead of dealing with increasing or decreasing functions, we're dealing with concavity. Now, this I'll give you as well. We covered this earlier when we were looking at max-min problems. This is second derivative test for critical numbers. So it's applied specifically for critical numbers. So you know all this. If the first derivative of a value x equal a, and then the first derivative, so this is a critical number, x equal a. Now, if the second derivative is positive, then a, I don't know why didn't italicize these, I should clean this up. But anyways, then a is going to be a local minimum. So this is what we did last time. So if you're checking critical numbers and you get a positive value for the second derivative, yeah, you get this. That's going to be a minimum. So this is how we can tell whether something's a min or a max. And then the same thing here. If we have a critical number right there, and the second derivative is less than 0, then a yields a local maximum. So the same thing as we saw earlier. So this is just a special case of the second derivative analysis. Now what's interesting here is if the first derivative is equal to 0 at x equal a, and then the second derivative is also equal to a, then it's inconclusive. And we're going to run into that. I'll look at an illustration of it fairly quickly. But it isn't that big of a deal. This just means that we have to do analysis, full second derivative analysis in order to see what's going on. So if you take a look at these two functions, this should make sense. We've seen similar ones before. On this cubic graph, first off, f prime at x is equal to 0 at that point. You don't believe me? Take the first and second derivative. F prime at x is equal to 3x squared. And then the second derivative, f double prime at x, is equal to 6x. Now you set them both to 0, and you're going to notice that in both cases there is the first derivative is equal to 0 at that point, and the second derivative is going to be equal to 0. So I'll say at x equals 0, more like it. And then on this graph, the second one, the first derivative is equal to 4x to the 3. The second derivative is equal to 12x squared. And in both cases, again, at x is equal to 0, the first derivative is equal to 0, and the second derivative is equal to 0. So what we're finding by inspection of these is that in this case, this represents a point of inflection. But in this case, this represents a minimum value. And mathematically, we were not able to tell. In both cases, the first derivative is equal to 0 at that point, and the second derivative is equal to 0. Yet in one case, that point, x equals 0, turned into a point of inflection, and then on the other, it turned into a minimum. So the question is, how do you tell? And the way you tell is first and second derivative analysis will show if x equals 0 is a min or a max, or a point of inflection. But just setting them to 0 won't be enough. If you did first derivative analysis, you would note that the function is increasing through, for this first one, the first derivative is always increasing. Or it's always positive, excuse me. So the first derivative is always positive. So there's not a change in direction. So therefore, it's a point of inflection. For the second graph, the first derivative is going to be changing from negative to positive. So therefore, it turns out to be a minimum. It's a lot easier to see on an equation, and it's actually fairly straightforward. So let's take a look at a few examples of that. So we want to find out points of inflection and discuss concavity of the following. So I'm not going to linger on the first derivative, but go right to the second derivative. But you always have to go through the first derivative. So f prime at x, 2/3 times 3 is just 2, so we get 2x squared minus 12x plus 16. Second derivative is equal to 4x minus 12. Now I'm going to note, before I get too deep into this, that the domain is all real numbers. It's a polynomial function. So if we want to do second derivative analysis, we look for the possible points of inflection. So I'll go PPOI. And that's going to be where the second derivative is equal to 0. So we take that 4x minus 12, we set it equal to 0, and we get 4x is equal to 12, so x is equal to 3. So that is a potential or a possible point of inflection. And then we do what we had been doing for first derivative analysis. We put this on our number line and we do interval analysis. Now I know what you're thinking with this 4x minus 12. It really isn't necessary because it's just a linear. And of course you're right. I'll do it anyways just for consistency's sake. But one factor of 4x minus 12, you could factor out a 4 if you wanted to. And then let's observe the behavior. So we have 3 being the potential point of inflection. And 4x minus 12, if you plugged in a number bigger than 3, will give you a positive value, just like it'll be negative to the left. So for this graph, if the second derivative is negative, it means that the function is concave down at that interval, in that interval. Just like if it's positive, it's going to be concave up. And that gives us all the information that we need for this. Discussing concavity, if you like. And the point of inflection, therefore, is going to be at x is equal to 3. Now, if you want to find out the value, you have to plug it in to the original. So f at 3 is equal to 2/3 times 3 cubed minus 6 times 3 squared plus 16 times 3 plus 1. And then just push that through your calculator if you like, or just get the number for it. It works out pretty well. I believe the answer would be 13. So f at 3 is equal to 13. I'll check that out. That's correct. So the point of inflection is at 3, 13. So let's take a look at the graph and see if we can make any sense out of this one. As I said, points of inflection are harder to note by inspection. It does take a trained eye. Max and min, had we set the first derivative equal to 0, then we would have identified the max and the min values. But what we got right here is at 3, 13, which is about right there, there is a point of inflection. So this really is concave down in this interval, and then it switches over to concave up. So the cup is down, the cup is up. So you do develop a sense for that. The slopes of the tangent line go from decreasing to increasing. So if you think of this in terms of motion problems, we're aligning this with acceleration. Let's do another one. Now this one's more complicated. It's a more difficult graph, or difficult function. And the first big problem is getting the domain right. And it is all real numbers. I know you're thinking that these are radicals, but this is the 5th root. And remember, you can take the 5th root of a negative number, so we can plug in any x value you want. And this matters quite a bit, the domain and range, or the domain. Now when we get the first derivative, I won't linger over it. When we start graphing these, of course, then we do have to pay attention. But here, I'll go 6 over 5x to the 1/5 plus 1 over 5 x to the negative 4/5. Now I know you're thinking, well, let's get a common denominator and see where it takes us. Well, again, we would normally do that if we were going to graph it or do anything with the first derivative. But I'm going to keep on going right to the second derivative, because that's what the question wanted. So 6 over 5 times 1 over 5 is 6 over 25, and then x to the negative 4/5, and then minus 4 over 25 x. Now when you subtract 5 over 5, you'll get minus 9 over 5. So here, because we're going to do analysis, we want to get a common denominator. It's always easier to have this thing expressed as one fraction over another, or one factor over another. Now, the common denominator, suppose I should probably throw in one other thing first. This could be written as 6 over 25, and then that's x to the 4/5 on the bottom, minus 4 over 25 again, and this time we have x to the 9 over 5 on the 9 over 5 on the bottom. So when we get a common denominator, the 25 will be there, the x will be there, but it's a matter of getting the right exponent for it. And the exponent would be 9 over 5. So we can bring that 4 over 5 to 9 over 5 pretty easily. We have a 6 already on top, but we have to multiply by x to the 5 over 5, which is x to the 1. So make sure you're careful with that step. You're bringing x to the 4/5 to x to the 5/5. And then the next one is the 4 is there already, and we don't need to do anything. It's already got the denominator of 25x to the 9/5. So we're set up. So potential points of inflection, I'll write that's what I call them. A few other people do. So you will run into that occasionally. First off, they're found where the second derivative is equal to 0. So as before, we concentrate on the numerator. So 0 is equal to 6x minus 4. 6x is equal to 4. So x is equal to 4 over 3, so 2/3. And then we deal with where the second derivative doesn't exist. Easy to lose these ones. But that's going to be the denominator. So 25x to the 9 over 5 is equal to 0. Divide by 25, and you can see where this one is going. X to the 9 over 5 is equal to 0. So x is equal to 0. Give a quick look to see whether that's in the given domain. It is, because the domain was all real numbers. And then that shows us we've got 2 points of inflection. Oops. This is making my interval analysis a little awkward. I can't get rid of that. Nothing we can do. Just have to deal with it. So you'll have to keep your work a little neater than mine. X is equal to 0 is 1 point of inflection. X is equal to 2/3 is the other, possible points of inflection. See, this is one where we have to be careful, because we didn't do the first derivative, but it's very likely that the first derivative also there's a critical number at x equals 0. So that's going to be the one that's going to be a problem for us. But everything will get revealed in this step. So we have 6x minus 4. We have 25x to the 9 over 5. And we have the second derivative right there. Now 6x minus 4, if you plugged in an x value bigger than 2/3, it will be positive to the right and then negative to the left all the way down forever. 25x to the 9/5. Now be really, really careful with this one, because if you pick an x value greater than 0, take the 5th root and then raise it to the 9, it's going to be positive still. So it will be positive to the right. If that had been 8 over 5, it would have still been positive, but it would have been positive everywhere. And if you picked a negative number, a little tight there, but it's a negative number, then it will remain negative. The fifth root of a negative is negative. Raised to the exponent of 9 is still negative. So the second derivative is going to be positive there, it's going to be negative there, it's going to be positive there. So where it's positive, it's concave up. Where it's negative, it's concave down, and then positive again, concave up. So we in fact do have points of inflection at x equals 0, x equal 2/3. So it changes from concave up to concave down at 0. It changes from concave down to concave up at 2/3. And of course you're wondering, well, what are those coordinates? So f at 0 we plug into the original 0 to the 6 over 5 plus 0 to the 1 over 5. So f at 0 is equal to 0. So 0, comma 0. And then the next one, f at 2/3. Well, did I give instructions for rounding on this one? Can't remember, but I think we better take this one to the nearest decimal, because that's going to be a nasty one. So f at 2/3 would be equal to 2/3 to the 6 over 5 plus 2/3 to the 1 over 5. So I'm just going to run that through my calculator, cheat a little bit. So 2 divided by 3 in the bracket, raised to the exponent of open bracket 6 divided by 5 plus 2 divided by 3 raised to the exponent of 1 divided by 5. And I'm getting 1.5. So let's keep it like that. This is not the way you normally like to do things, but I'm going to keep it as 1.5. So 0, 0, and I'll write that in decimal form, 0.67. So I'll be consistent, 1.54. So these are our 2 points of inflection. And when we do start graphing them, we'll note them, and then we'll also note the intervals where it's concave up and concave down. And then let's take a look at this, and let's see if that matches. According to this, not a great diagram, but x equals 0, this is definitely going to be concave up until we get there. Now this graph is exceptionally tight around the axis, but it is concave up for that interval, so it clearly changes from concave up to concave down. And what you probably can't tell on this graph is that this is not a linear graph. It changes back to concave up again there. So you can see a slight curve. Very difficult to recognize where it's happening, but it looks like there's that point of inflection around 2/3. So by changing the scale, you probably could get that worked out. But this is a really, really tight graph around the axis. But the numbers won't lie. So that'll take care of this lesson. In the next lesson, we'll start just graphing these and putting everything together, all the asymptotes, the symmetries, the x and y intercepts, and then first, second derivative analysis. Thank you for your time.